this one. Okay, so for page 3, same picture that we had in packet 1, we've got there we go. We've got this beam or bridge, rod, whatever you want to call it. It's got a particular length and mass given. Now it's initially held by a string, but when the string is cut, no more tension, no more support. What's this rod going to do? It's going to rotate, fall down, right? Now we did one similar with a person on, and we just said, what's that initial angular acceleration? Well, the question today, what's the angular velocity when it's at the vertical? So in the future, isn't it true that maybe it looks like this? So it's going to rotate, okay? So we'll call that clockwise, the positive direction. Is it going to rotate at a constant angular velocity? No, that would mean it has no angular acceleration, but hopefully you know that there's still going to be torque on it and it's going to have angular acceleration. Now, many of you may say, well, I still want to go the torque approach, torque kinematics. I'm going to take energy, but here's the problem with the torque approach. And so on the side, okay, if you start horizontal, but then maybe later you end up at some other, right? Look at your center of mass, because you would look at the torque done by gravity. Well, when you get closer to the wall, that same force, those two are the same forces, but their location is different, right? And so the difference, the problem with torque, R perp G in the beginning, is not the same. Yes, I drew a horizontal. We would need an angle at the point, right? And so R perp G is not constant, which means the torque of gravity is not constant, which means your alpha is not constant. And so even if you said, I want to go torque and angular acceleration or kinematics approach, you'll run into an issue. That lever arm is constantly changing. And so let's take the energy approach, not the torque approach. And so with energy, you need that initial position. I'm going to go with the straight horizontal as initial. And then final is going to be the straight up and down. Okay, whether it hits a wall or just swings through, that's where we stop the clock. That's where we are going to pause. And so what's the angular velocity when it's at the vertical? And so, yeah, it's going to start out with 0. So the initial is 0, and then it's going to swing down. Well, where does this speed, angular speed, come from? Think energy. Do you see a height change? Now be careful. What point are we looking at? What's the only real consistent point, if it's the rod alone, that we can look at? The center of mass. And so come in here, the center of mass, gravitational force, right? Now our energy isn't going to do that gravitational, potential energy kind of does. But where does the center of mass end up? Well, it's still in the center of the rod, center of mass. And so if we notice, there's a height change for that center of mass. What is the height change? Not number, what is it in terms of the length? Half the length is the height change, okay? So be careful, you may be tempted to use the full length for this height change, but you're looking at just that center of mass location. And so really we're focused on the center of mass's rotation here. And so what would our energy statement read? Well, up there when it's straight horizontal, no initial velocities of any kind, it has potential energy, mgh. equals. Well, as it rotates and falls downward, it's going to rotate. So 1/2 I omega squared, but it still has a tangent velocity. And so don't forget, you have a tangent linear speed to the circular path. And so we're still going to write that translational 1/2 mv squared. Now, a couple things here. They want the angular velocity, so we can keep our omega and do the non-slip. Yes, we're going to do non-slip. We'll assume that the hinge, by the way, this is pretty common, the hinge is frictionless, okay? And so there's no energy losses. Every time it rotates, it's going to have that linear motion change. And so with non-slip, we'll say that v squared equals omega squared r squared. So we can plug in the non-slip equation for the linear velocity, since ultimately they said, what's the angular? Now, yesterday, I ended up solving, I plugged in what we were used to. I ended up solving for the linear velocity, and then you just backtrack with radius to get omega, okay? So it's not hard if you sub in the wrong one to begin. And we also need to know the inertia of this rod. Again, you don't have to memorize it, but the inertia of the rod with the fixed end on one end is 1/3 ml squared, okay? Now, yesterday I got going real quick and I said 1/3 mr squared and r's canceled and everybody was good. But technically, rods, that 1/3 is based on L. So FYI, we're going to use L. Everybody good? All right, let's plug in. And so MGH equals 1/2 times 1/3 ml squared times omega squared. I'm keeping it. That's what we're solving for. Plus 1/2 m. And now, in place of the linear velocity, I'm going to plug in omega squared r squared. What do we notice happens? R's don't cancel, but what does? M. You can cancel. Ooh, what happened there? Hold on. That was page 3. Okay. And so M's cancel. Even though they gave you the mass, you don't have to cancel, but you can. And so now we're going to plug in some things we know, okay? And then try to combine, factor out omega squared, solve for omega. So it's maybe 2 or 3 more steps. And so G is 10, the height change. Now, technically, I didn't involve a final height because if you remember potential energy, it's their lowest point for the center of mass. So what could I call final height? 0, right? It's not the lowest point on the rod, but it's the lowest point for that center of mass that we're focused on. And so that initial height is equal to L over 2. If you go back up, L over 2 is, L is 2. I know that reduces to 1, but just putting it in for format. Height is L over 2, length is 2. And then we got 1/2 times 1/3. Length is 2. Don't forget to square. Oop, not equals. And then we have omega squared. And then we get 1/2 of omega squared. Now, what's this R? Well, this is that R for the center of mass. So go back up. What's the radius that the center of mass has? 1/2 of L. So it's going to be that 1 value again. And so now we have, it's just math now, right? We've got 1 variable, omega. It is in 2 places, but let's simplify the numbers. And so we get 10 equals, and then we'd have 2 squared 4. 1/2 of 4 is 2 divided by 3. So we'd get 2/3 omega squared plus 1/2 omega squared. So factor out omega squared. And so 2/3 is like 4/6, right? Common denominator. And so we get 7/6. And then 60/7. And final step, square root. So what do we get? 60/7 is 2.96, so about 3. And the SI unit for angular velocity. Right, and so, sometimes I throw the units in when it's easy enough. Here, there were so many steps, so many combinations. Moral of the story, if you start SI, you should end SI, okay? As long as you plug it in the calculator right. And so 3 radians per second is what they asked. Now they say, what's the linear speed for a point 1.5 meters from the hinge? And so we could figure out the tangent velocity of the center of mass for the tip of the length of the rod, or pick some other spot. What color have I not used? Green. What about this spot? Okay, so at the 1.5 meter mark from the fulcrum, is it going to have the same linear speed as the center of mass? Is it going to have the same angular speed as the center of mass? It's going to sweep the same half pi in the same amount of time. And so it's this concept that the omega for your center of mass is the same omega for the 1.5 mark, and it's the same omega for the edge of the rod. Omega is the same no matter what part of the rod you're looking at. But if you have a different radius, you have a different linear speed, right? We talked about that concept back with circular motion. And so using our non-slip equation, V equals omega R. And so for the 1.5 mark is what we're trying to look at. We'll use the same omega 3 radians per second times 1.5 meters. And so what do we get here? 4.5, and what's our unit? Yeah, so now that meters is here, we don't need radians anymore, right? It's not a physics unit, it's a placeholder unit to use as needed. And so 4.5. If they wanted the edge of the rod, you'd multiply by 2. If they wanted the center of mass, you'd multiply by 1. Good deal? Okay. Questions on page 3.